It happened within seconds. The ground beneath my feet trembled with a force rising from deep within the earth. Buildings leaned, walls cracked, roads split apart. But this rupture was not just a matter of a few seconds. It was the sudden release of energy that had been building for years, deep within our planet. To understand this process, we must rewind time to the very beginning, to the first moment when Earth was newly born, and its surface was still covered with magma. Around 4.5 billion years ago, the solar nebula collapsed. At the center, a young star began to form. The remaining material continued to rotate, creating a vast protoplanetary disk. This disk consisted of light gases, fine dust particles, and frozen fragments of ice. Over time, these materials collided, merged, and gradually formed the planet we now call Earth. After Earth formed, meteorites struck the young planet again and again. At the same time, radioactive decay within the core generated enormous heat. Together, these forces transformed Earth's surface into a vast ocean of magma, covered with molten lava. Under this intense heat, the formation of a solid crust was delayed for a very long time. But gradually, meteorite bombardment from space began to decrease. Radioactive decay also slowed. As a result, the surface temperature of Earth began to fall. The magma oceans slowly cooled. Eventually, Earth's first crust began to form. Yet this early crust was extremely thin and fragile. Compared with the thick and stable tectonic plates that form today's continents, it was delicate and unstable. Beneath this crust, the mantle remained hot and dynamic. Material deep inside the mantle was constantly moving in a slow, continuous cycle. This movement is known as convection. Hot material rises upward, then cools and sinks back down into the depths. These convection currents placed enormous stress on the crust. They stretched it, fractured it, and eventually broke it apart. As a result, around 3.2 billion years ago, Earth's outer shell, the lithosphere, split into large moving plates. This separation initiated the dynamic system we call plate tectonics. Over time, these plates moved in different directions. When plates moved away from each other, magma rose from below to fill the gap, creating new oceanic crust. The ocean floor slowly expanded. When plates collided, one plate was forced beneath another. This process formed thrust faults and raised massive mountain ranges. And when plates slid past one another, strike-slip faults developed. Each type of plate boundary created different stresses within Earth's crust. Over long periods of time, these stresses allowed enormous seismic energy to accumulate deep underground, and this movement continues today. Tectonic plates are always moving, but extremely slowly. However, this motion cannot pass smoothly through the rocks along plate boundaries, because friction between the surfaces blocks the movement. When movement is prevented, stress begins to build. Rocks can tolerate this stress for a while, thanks to their elastic nature. They stretch, they bend, and they store energy within their structure, like a compressed spring, waiting to release. This temporary change in shape is known as elastic deformation, but no rock can endure forever. Eventually, it reaches its breaking point, and when that moment arrives, the accumulated stress exceeds the critical limit. Kilometers beneath the surface, energy that has been silently building for years can no longer be contained. Suddenly, a rupture occurs at the hypocenter, and the earthquake begins. The hypocenter is the point where the rupture starts. It is the true focus of the earthquake. This point usually lies several to tens of kilometers beneath Earth's surface. From this point forward, the rupture spreads rapidly. It moves along the fault line at speeds of several kilometers per second. A rupture front forms, and the elastic energy stored for years is suddenly released. The magnitude of an earthquake depends on several factors: how large an area the rupture spreads across, how much the plates slip past each other, and how rigid the surrounding rocks are. The strongest shaking occurs directly above the hypocenter. This point on the surface is called the epicenter. Here, the energy rising from Earth's depths reaches the surface directly. For this reason, the shaking is usually felt most strongly at this location. Another factor influencing intensity is the distance between the hypocenter and the epicenter. This distance is known as the focal depth. The shallower the earthquake focus, the less energy is lost before reaching the surface. That is why shallow earthquakes are often far more destructive. As the rupture spreads along the fault, the released energy travels outward in the form of seismic waves. The first waves to arrive are the fastest. These are the primary waves, or P waves. They travel at speeds of about 6 to 8 kilometers per second. P waves carry the very first vibrations of an earthquake. They move through matter by compressing and expanding it, much like an accordion. As rocks along the fault compress and expand, these waves spread rapidly outward. P waves can travel through solids, liquids, and even gases. Because of this, they are the fastest seismic waves. Soon after, secondary waves arrive. These are known as S waves, or shear waves. They travel more slowly, at around 3 to 4 kilometers per second. Unlike P waves, S waves move particles perpendicular to the direction of travel. The motion resembles a rope being shaken from side to side, or up and down. This creates powerful lateral shaking in the ground. As S waves pass through solid rock, they generate enormous structural stresses. However, liquids cannot transmit this type of motion. For that reason, S waves can travel only through solid materials. The first cracks and the first structural failures often occur when these waves arrive. But the most destructive motion comes from waves trapped near Earth's surface. Love waves are one example. They move in a horizontal motion similar to the twisting movement of a snake. As they pass, they drag the ground from side to side. This movement can shift building foundations and destabilize structures. Then come Rayleigh waves. Their motion resembles waves rolling across the surface of water. These waves form when P and S waves reflect and refract along Earth's surface. Rayleigh waves move the ground both upward and downward, in a rolling elliptical motion. They typically travel at speeds between 2 and 4 kilometers per second. Their long wavelengths and low frequencies can resonate with tall structures. In other words, the rhythm of the waves matches the natural vibration frequency of a building. When this happens, the shaking is amplified, and in some cases, buildings collapse. When seismic waves reach the surface, their impact also depends on the type of ground. On solid bedrock, waves travel quickly. The shaking lasts a shorter time, and damage is often limited. But in loose soil layers, the situation can be very different. Here, the amplitude of the waves can increase dramatically. This effect is known as ground amplification. In valleys filled with soft alluvial sediments, waves slow down. Energy accumulates, and the shaking may be felt several times stronger. In some areas, another dangerous process occurs: liquefaction. In water-saturated sandy soils, intense shaking causes the ground to temporarily behave like a liquid. When this happens, the soil loses its strength. Buildings may tilt, sink, or collapse. Eventually, the main shock passes, but the stress along the fault has not completely disappeared. Around the fractured region, stresses begin to readjust. The crust has not yet returned to equilibrium. This imbalance triggers a sequence of aftershocks. One after another, smaller earthquakes follow. According to experts, these tremors may continue until the crust fully stabilizes. Deep beneath us, the heart of the Earth keeps beating. Tectonic plates move only a few centimeters each year, yet over time, they reshape the entire surface of our planet. The earthquake we experience today was only a brief moment in this movement that has lasted billions of years. And this movement will continue, because Earth is still changing, and we must learn to live in rhythm with our planet.